To talk about habitat as habitat, how temperate marine fishes move around artificial and natural reefs. Chris.
Okay, so good morning. So the talk I'm going to present today is kind of 20 years of data that we've collected across a bunch of different projects, looking at behaviors of fishes associated with natural reefs and those associated with artificial reefs. And the bottom line is ecologists have been trying to get at the characters that we think are important for fish, especially for reef fish. What are those key reef habitat characters? So many previous fish ecology studies have identified a variety of characters that we think are important key habitats. So for example, for the benthos, things like vertical relief, high rugosity, all those things are very important, and the substratum type itself are very important for increasing species diversity, abundance, and biomass. Of course, things like wave energy, water temperature, salinity, all of those environmental variables can also affect how those benthos factors can affect species diversity and abundance. And then, of course, there are things that are growing on that substratum, whether it be rock or coral. You can have algal height, algal composition, and density that can also affect that complexity. So the bottom line is most of the work has been focused on the community structures and the species associated with those communities and how those different variables can shape or build those communities, but there's been a lot less work focused on how animals use those habitats and how that affects their behavior, their habitat selections, and their space use. So we've actually proposed some models where looking at affinity for certain habitat types and more complex substrata, that species should have smaller daily space use. And this comes back to what John was talking about, right? So you have a highly complex habitat. Individuals need that habitat for structure, for hidey holes, things like that, but it also provides food. So as a result, you would expect species associated with high affinity for that substratum to have very small space use, mainly because they're tied to that space. They can't venture far. But now we get to species out on a relatively flat substrata. Now we should expect them to require more space use. So we should expect their daily space use to go up because their food availability actually is more spread out. And then we can eventually get to open ocean species that may be completely nomadic. They show very little affinity to any complex substratum at all. So by using this model, we can begin to test hypotheses on what we should expect to see based on where we find certain species. So when it comes to artificial reefs, typically the concept there is you're putting structure in a place where there typically hasn't been structure. You're creating structure. And like the old movie saying is, if you build it, they will come, that phenomenon has been shown over and over and over again. You put a block on a flat, sandy area, and fish show up the next day. So when we start looking at the characteristics that should help shape that habitat, it's, once again, things like benthos. It's the substrata type. It's the vertical relief, it's the rugosity, as John was coming back to, that fractal component of the habitat that probably makes it more attractive to certain species. And then, of course, you have substrata for which things can grow and provide a food source or cover. So some artificial reefs are specifically developed to try to mimic that natural habitat, right, based on those mature communities. And in other cases, they're kind of unintentionally doing that. Things like shipwrecks form that unintentional habitat. So the question that fish behaviorists always want to know, are fish using that artificial habitat in much the same way they do natural habitat? And of course, the problem there is, in many ways, we're looking at this from a restoration ecology standpoint. Because new reef that goes in doesn't have a fully developed, mature community associated with it, so it's going to change over time. So a lot of that behavior will change depending on how that environment changes and progresses as the communities grow. So now we have to talk about the difference between structure and function. So quite often when we put artificial reefs in, the way we assess them is based on standard transecting techniques. So you go out and you count who's there, you assess who's there, you look at how many are there, and that gives us some indication of the structural metrics of where that artificial reef is in its progression. How close is it to a mature natural reef in its community structure? So these surveys quite often are static. You can't be out there surveying 24/7. So you have points in time where you're getting snapshots of what the populations are doing. And of course, it's really, when it comes to understanding behavior, requires more dynamic sampling. You constantly have to be looking at what individuals are doing and how they're responding to those aspects of the habitat and changes the community around them. So quite often people have gone out and attempted to do this in terms of monitoring production in various artificial and natural reefs. But the problem comes down to functionality. So when we want to look at functionality of artificial reefs, just like we do at natural reefs, what we really have to focus on is functional metrics. And those are, just because you go out and count a fish there doesn't mean it's actually staying there and using the habitat. So when it comes to measuring those functional metrics, maybe we should be using things like site fidelity. If an individual's there one day and it stays there for 3 months or 6 years, that tells us that they must be using something from that habitat. Another thing may be the amount of space they use. So if there are fewer resources, the individual may use the reef as refuge, but now has to venture further to get adequate resources, which, as John points out, puts them at risk from predation. So we can use these as functional metrics to evaluate how fish are using these various habitats, comparing natural reefs with artificial reefs. So one of the ways we go about doing these, measuring these functional metrics, are using tools like acoustic telemetry. They give us that dynamic sampling where we can monitor individuals over periods of time and look for patterns of behavior among individuals. So we can look at things like space use, rate of movement. We can look at habitat selection, site fidelity, habitat connectivity using these tools, but there are a variety of different telemetry tools that we can use. And of course, they all give us different measures of resolution, which pose challenges when we're making comparisons. And of course, the methods matter. So for example, the old school active tracking, you put a transmitter on a fish, you follow it around, you sit in a boat, you get high resolution information of where the animal is. You can only generally track one individual at a time, but you can get at habitat preferences. What habitat is that fish associated with at this time of day, and another period of time? And of course, you can only do this for days to months, right? It's exhausting work. But you get very high resolution information on individuals. The other tool that's become far more popular is passive tracking. Basically, you're putting out acoustic receivers. You can have a variety of receivers out. You can now track individuals from days to years, even decades now. You can tag and track multiple individuals simultaneously, but really what you're getting at is presence-absence. So you don't know exactly where that animal is, you just know it's within detection range of a receiver. So it gives you lower spatial resolution, which may not really help you get at habitat preference, but it can get at things like site fidelity. So back in the early 2000s, we started tracking reef fish in a marine protected area around natural habitat. And working in marine protected areas are great because you're working in a habitat that's less influenced by human activity, like fishing. So here we track calico bass. This is a popular sport fish in California. And the polygons you see represent home ranges that we determined for individuals over a period of up to a month. As you can see, these home ranges are fairly small. If we compare that with another species, a wrasse, local wrasse species, also a game fish in California, we see sheephead use different size home ranges on different type habitats than they do in other type of habitats. So the bottom line is different species are using different habitat types, have preferences for different habitats, and the amount of space they use vary depending on that habitat type. So when we compare those average space uses over the course of a month for all these different species, we find things like ocean whitefish, California sheephead, which are benthic foragers, have larger home ranges than ambush predators like calico bass and barred sand bass. Now, barred sand bass are also known to seasonally migrate, form spawning migrations. But if we just look at their daily space use, we can begin to get a handle on how much space the individuals need, whether it be natural habitat or even artificially associated habitat. So now to get to methods. So a colleague, James Lindholm and colleagues, tagged a bunch of sheephead around Anacapa Island, neighboring island. Using passive acoustic telemetry, they found that males used larger home ranges than females, but also these were 2 orders of magnitude than what we had measured using active tracking at Catalina. So part of this is an artifact of the method, right? So we don't know exactly where those fish are, but you're encompassing all those receivers. Chances are you're overestimating to a certain extent. But also they're able to track individuals over a period of 2 years. So obviously the amount of space they're using may be shifting. So your estimate of space use may actually be more accurate than it would be if you're just actively tracking like we are. So the bottom line is we have to be careful about how we use some of the methods in making comparisons between studies for the exact same species. So what we've actually done is for the same species that we actively tracked, we also passively tracked in this little marine protected area around natural habitat. So we have these acoustic receivers, the rings you see are detection ranges, And we tagged 20 ocean whitefish, 20 kelp bass, 20 sheephead, and 8 barred sand bass in that area to look at fidelity to those home ranges that we measured using active tracking. And what we found was over a 1-year period, a vast majority of these fish were detected on a daily basis within the areas from which they were actively tracked, showing high site fidelity to those home range habitats. So in other words, in high quality natural habitat, these fish are homebodies. They're home ranging species. So one of the other interesting things we found when we looked at the fine scale habitat was none of that kelp bass or sheephead that we had tracked ever crossed this area to these other natural reefs that are literally 200 meters apart. So these are across a deeper sand channel. So we decided, well, let's translocate fish. Let's take fish from their home ranges. We're going to take some of these fish about 2 kilometers away across this sand expanse. And other individuals we're going to translocate across continuous habitat and ask how long will they come back to their home range and how long will it take them. So 80% of the barred sand bass and ocean whitefish that we translocated 2 kilometers away were back to their home range in hours after translocation. So crossing sand habitat was no problem for them. Individuals that we translocated to continuous habitat could rapidly return back, and that was the case for barred sand bass and sheephead. But kelp bass and sheephead that we translocated out here took weeks to months to return if they returned at all. So it began to show us how habitat barriers, like sand expanses, may be barriers due to predation risk. So recently we've been working on the Wheeler North Artificial Reef, and Steve's going to be talking a lot more about this reef. It's a large mitigation reef built in 2008. It was a mitigation reef to replace lost kelp habitat from a kelp bed off San Onofre, where about 150 acres of kelp were lost and about 28 tons of fish were believed to be lost as a result. So 125 tons of quarry rock were brought in to create reef modules covering about 2.5 square kilometers of habitat. So this is a big artificial reef. So this reef has been fairly well studied. It's been annually studied. In fact, there were work done before the reef was put in place, so there's opportunities to look at before and after. And of course, all the neighboring natural reefs have also been studied. Things like kelp density, invertebrates, fish species, richness, recruitment, production has been intensively studied over the last 10 years since this reef's been put in place. In addition, there have been great comparisons to all the natural reefs that exist in the area, so it provides a great experimental habitat to begin to look at fish abundance. However, most of these have been static measurements. So if we come back to the functional metric about how fish are using that habitat, there really wasn't any good information on that. So our questions were, are fish, particularly game fish, the same ones that we attract in natural habitat, are those fish show high fidelity to those habitats? Are they show home ranging behavior? And are they show seasonal migrations along that natural reef or the artificial reef? And do they migrate or immigrate to any of the natural reefs, as is hypothesized by the attraction hypothesis? So we studied kelp bass, barred sand bass, and sheephead, the same species that we had studied previously in natural habitat. So to do this, we laid out 38 acoustic receivers throughout this habitat. We had 6 receivers on what we call brackets to determine migration habitat. So we basically had the entire reef encapsulated with acoustic receivers. We estimate about a 200-meter detection range. We tagged 45 fish of each species on the reef, and the assumption was that if we tagged them on the reef, we would be able to detect them if they remain there. So in addition, there are 3 reefs moving away south from there, one San Mateo, which is literally almost habitat connected to the artificial reef, and about 7.5 kilometers away is the San Onofre Reef. That was the one that was affected by the nuclear power plant that this habitat was mitigated for, and then another reef called Barn Reef, which is further away. Now, unfortunately, we tagged 20 fish on each one of these natural reefs, but we could only afford to put 1 receiver on each of the reefs. So we couldn't have enough receiver coverage to cover it the same way we did the artificial reef, but the goal was to determine whether fish tagged here would go here, or whether any of the fish tagged here would go here. So if we look at the site fidelity of these species, we find that California sheephead showed relatively high site fidelity. In fact, about 72% of the days they were detected in the areas where we tagged them. So on the overall artificial reef, 72% were regularly detected. When we look at kelp bass, we see that that number drops off steadily over time. And the same phenomenon was seen for barred sand bass, but we saw these seasonal dips where individuals left the reef but then returned to the reef. But nonetheless, we saw emigration away from the reef for these 2 species. Now, what was really interesting is we didn't see that from the fish that we studied in the natural habitat at Catalina, but one of the things that happened during the period of our study was a strong El Nino, and that killed off most of the kelp. So there was a major loss of that vertical relief on this habitat. So we see that between 2014, when we started the study, and 2015, a major loss of habitat. In fact, there was a significant reduction in kelp, and we think that contributed to a bulk of that emigration for kelp bass and barred sand bass. When we look at the sizes of the fish relative to their likelihood of staying, we saw that there was no relationship between size and their degree of site fidelity for female sheephead, male sheephead, or kelp bass. But what was really interesting is barred sand bass showed a positive relationship. In other words, larger individuals were more likely to stay at the artificial reef despite the loss of kelp than smaller individuals. So we could also break the reef down into smaller components, home range size components. And we broke this into 6 sections. And then basically we tracked individuals that were tagged in each section. So for sheephead, 82% showed high fidelity to the zone which they were tagged. In other words, they showed high home range fidelity. So if you look at the colors, just following the colors, you'll see most of the individuals remained in the colored zone from which they were tagged over the course of the 1-year study period for those that we were able to track. The same was true for kelp bass. Those that remained showed high fidelity to the zones that they remained in. So in other words, their home ranges didn't expand. They stayed in that same amount of area. And the same was true for barred sand bass. So at this way, we're able to kind of get at home range size. But what was really interesting is looking at their propensity to stay or leave. So using a network analysis, the thicker the bar means the more transitions that occurred between individuals for those tagged on Wheeler Artificial Reef and those moving to Trestles, which was the next closest. So what we see is the further away you get, very few fish were leaving the artificial reef and going to any of these other natural reef habitats. So the natural reef habitats weren't stealing fish back. But what was really interesting is when we looked at fish tagged on natural reefs, very few of those fish were actually leaving to go to the artificial reef. In fact, the greatest exchange we saw was between San Mateo and Trestles, with a little bit of exchange between Wheeler North. Now remember, we documented a lot of fish leaving the reef, but when they were leaving the artificial reef, they weren't going to these natural reefs. So that tells us a lot about this attraction, production sort of concept. Once fish hit that reef, by and large, they're there. But as John was pointing out, many of those factors about habitat may influence who stays and who goes. Now quickly, I want to talk a little bit about some of our other artificial reef work, which is on offshore platforms in California. So the same questions and debates exist. We know that they recruit fish. Typically, they recruit the upper parts of the platform. You get stratification of size class. And of course, we find larger fish and more fish on platforms than you do on neighboring natural reefs. The question is, do those fish stay? So we did the same thing. We tagged fish on these artificial reefs, these offshore oil platforms, and we monitored their site fidelity over a 2-year period. So what we see is that some species show high site fidelity and others don't. For those that did show emigration away, what we saw them moving from shallower platforms to deeper platforms before they completely left platforms altogether. In addition, we actually translocated fish off platforms. We took them off platforms and translocated them to natural habitat. And those fish are basically in a marine protected area. And what we found was that 79 of the fish that we took off of 12 species that we translocated here, we also took 19 fish off a deep reef and translocated them to these platforms. And what we found was, of the fish that we took off the platforms, 9 of the 10 lingcod that we took off the platforms to natural habitat returned back to the platforms, some cases in 10 hours. Other species showed homing back to the platforms. Overall, 25% of the fish returned. For the fish that we took off the natural reefs and put on platforms, only 16% returned back to a natural reef, even though that natural reef was closer. So the bottom line is, clearly not all habitat is equal, but some of this artificial reef habitat, at least the way the fish are acting, appears to be functioning in much the same way as natural reef habitat. Obviously, the maturity of the community around those artificial reefs do matter. And obviously, those key habitat characteristics like vertical relief, rugosity, and community structure are very important. So obviously, monitoring behavior as well as community structure are very important aspects that we need to monitor, as John points out, to get at things like mortality, fishing mortality. So with that, thank you.